Denise. Perdón. Today.
There is another one.
Yeah.
Olá, oi. Só uma coisa para lembrar. Hoje à noite tem a palestra da Rosalie Lopes sobre a missão espacial Cassini, a Saturno e as luas. Ali fora tem um papel onde podem colocar o nome para reservar os lugares, porque tem só uma parte dos lugares será para o público. Então, se vocês quiserem ir, que nós todos aconselhamos, é bom ir ali fora, assinar o papel, deixar o vosso nome, assim podemos reservar os lugares para os participantes da escola. Ok?
Okay, welcome back everyone. Good morning. So today we have the second lecture, Dr. Laura Perez, and she will continue talking about protoplanetary disks and early stages of planet formation. If you have any questions, please stop Laura and ask during the lecture, but we have, Ellen has the microphone there, but we have time for questions at the end of the lecture. So welcome back, Laura.
Thank you. Thank you so much. I hope, is this okay? Can you hear me fine with the new microphone? Okay. Yes, feel free to interrupt at any point. And the idea then of this lecture will be to now focus more on the protoplanetary disk side. And before I continue, there is some material here from some of the big shots in the field as well, Leonardo Testi, Jonathan Williams, Sean Andrews, Andrea Isella, Bernstein, Till Bernstein. So you will see some beautiful diagrams and slides that I have, that I thank them for providing. And so on the second day, the idea is to now talk about the era of ALMA in planet formation studies and show just a little bit of a flavor of how the field has changed now that we have ALMA. And to begin, we will define in a better way what we talk about when we talk about protoplanetary disks. And we will talk about the first steps towards making a planet, which is growth of the solids. We call it grain growth. And it's really how you transform the solids in the interstellar medium into the rocky cores of planets, into something like our own Earth, for example. And we will talk then about the first steps towards that. And tomorrow, we will talk about the later stages, okay? And then before going into beautiful ALMA pictures, which some of them are here, here's one, another, the famous HL Tau, that will be tomorrow, the beautiful ALMA pictures. We will just talk about what do we know from ALMA looking at surveys, so large quantities of disks, and what can we learn from that. So maybe we don't need such a high angular resolution. Maybe we need to look at a large number of disks, and ALMA can let you do that because it has very high sensitivity. So you can look at a huge number of disks in one go with only seconds sometimes integrated on source, so only seconds on every young star, and get an idea of a census of the solid material present or the gaseous material present, etc. Okay, so this is day 2, and at the end, I'll just highlight some of the open problems throughout the talk as well, and future studies. And so yesterday, we had this lovely picture of how it all began to make planets around low mass protostars. We need to link this to the protostellar formation process. But today, we will just focus on these objects that are full of dust, and we will look at their evolution and growth. We will look that the dust does not sit by itself in the disk. It's surrounded by a huge amount of gas, and their interaction causes some dangers for particles that become large. A pebble, so like a little rock. A little rock will interact with the gaseous medium and will suffer some problems. And so there are some dangers that we will discuss about. And then when we look at many, many objects, we will talk about disk survey. And to put everything in context, let's just talk about what is a protoplanetary disk. And really, is the birthplace of planets. That's what they are. And so they have the central protostar, and we talked about the protostar on Monday, on the first lecture. And they're surrounded by this disk, and we will talk about what's the difference in mass between the central object and the disk, and what do we see for the entire sample, and if there are any correlations. But the disk mass is lower than the central protostar mass. So the dynamics is mostly dominated by Keplerian dynamics around this massive object. And so this disk is circumstellar and is composed of gas and solid. The gas is mostly molecular hydrogen, is the most abundant molecule there, and molecules can survive in this dense environment. The problem is, as I said before, it's not so easy to detect this molecule, and so we use other tracers of the gas component. And these are, of course, much less abundant than molecular hydrogen. And the most common molecule used is, of course, CO, and the isotopologues of CO. The issues are that these molecules can evolve in different ways chemically. They can get linked and from the gaseous vapor phase into the solid phase, becoming ices, or they can transform, and so they go out of the gas phase, or they can transform chemically into more complex molecules, and so we don't also see CO because it interacts with other things. And so this is a big issue. Measuring the mass content of these objects is not straightforward, because whatever molecule we decide to use could be doing things that we don't really know if it's a good tracer of the bulk mass of the disk. And this is why we use dust as another tracer for the disk mass. The solid component, then, it's composed from interstellar medium-sized particles all the way to large bodies, planetesimals, kilometer sizes, and maybe even rocky planets in some of these objects, because some of the substructures that we see tell us already that there are massive bodies, that there could be massive bodies orbiting them. And generally, the composition, we mostly know about it from spectroscopy, very close to a central protostar, where you can heat up some of these solids and release them to the gas phase, and you can figure out some of the components of these dust particles, of these solids. But generally, silicates are like the surface of Earth, compounds with carbon, and ices of the different molecular species. And because this protostar heats up the surrounding environment, and it will very heavily depend on how close you are to the central protostar, what's the temperature at that location. And so there are these temperature gradients where the temperature will be quite hot closer to the protostar and quite cold further out. So we're talking about the sublimation temperature of the solids, so thousands of Kelvin, all the way, so very close to the protostar, all the way to the far outermost regions where it could be, a few to 10 Kelvin, something like that, several to 10 Kelvin. And so there's this temperature gradient, and there is also a gradient in surface density, a gradient in the amount of material. And so here I showed before what type of surface density we expect, but because this disk is feeding the protostar, because remember when we talked about it on Monday, the protostar is growing, being fed by this disk, and that means that there is much more density closer into the star than farther out. And so there's also a gradient in surface density from the innermost regions to the outermost regions. So higher densities and higher temperatures as we get closer. And so yesterday I showed this to show that, for this range of surface densities, which is what we expect from the innermost parts of protoplanetary disks, so the high densities, all the way to the outermost parts, we will expect that some of the, depending on the wavelength, some of the material will be optically thick completely, even at the longer wavelengths, or some of that material will be optically thin, even at, sorry, not even, but optically thin at the longer wavelengths. And this is why we like to look at, centimeter, millimeter, and centimeter, so where ALMA and VLA can probe, because at least in the outermost regions of the disk, we know that the emission is optically thin. And so we can probe the bulk of the material. And this density and temperature gradient then creates different, a different spectral energy distribution. And we can use multi-wavelength observations then to probe different regions in the disk. So closer into the star, as I said, it will be much hotter than farther out, where it will be colder and then much, much colder. And so you can imagine that the black body function that probes the inner disk will peak at very short wavelengths. And as the disk gets colder and colder, further out, this black body function will peak at longer and longer wavelengths. And so this is what is shown here. This is the sum of all these different black bodies that move from short wavelengths to long wavelengths due to the temperature change, the temperature gradient, the fact that the disk is colder further out and warmer closer in. And there's not only that, so there's the issue of the temperature gradient, but there's also the issue of the density gradient. And because it's much more denser closer in and much less dense farther out, closer in you will be optically thick. And at the wavelengths that are probed by these high temperatures, near infrared, remember my diagram before, you will be in the optically thick regime. And so you will only be able to probe the outer layer of the disk, the top of the disk. Because at some point you reach the tau equal 1 surface, the surface where you cannot see further, okay? So it's like depending on wavelength. But as you go to longer and longer wavelengths, you see everything when you go to the radio domain. When you are so far out in wavelength, you can probe densities from closer in to farther out in the optically thin regime. And so this is why we want to go to ALMA, because we can probe the bulk of the masses of the disk. We see the emission from all of these solids, and there is no obscuration due to optical death. There's no lack of emission. And on top, sorry, and so this is the disk emission here, and of course we have the young star here. And so what you see always is this excess of emission from the stellar photospheric emission, which should be down here. And this is how at the beginning, without even taking a picture of these things, we knew there were disks around these young stars. Because although we expected the stellar photosphere, we saw this huge excess that was quite large for a broad range of wavelengths, which told us right away that there were black bodies emitting at different temperatures further and further out from the star. So this is why humans were very clever. Without ever knowing about having Hubble Space Telescope figures or images of these, or ALMA images of these objects, we knew from looking at the spectral energy distribution, and we made models to describe what the spectral energy distribution already told us about these objects. And why do we want to go to radio waves? To convince you one more time, well, let's look as a function of radius on the cumulative mass. So we start very close to a central star, and we start summing up the mass. And when we get to 100 AU, let's say, we have most of the mass. We've summed up all the mass. Well, because we're optically thick in short wavelengths, if we trace the cumulative flux, very quickly we reach 100% of the flux, because further out is way too cold to have any emission, that black body, to have any emission from the disk. And so really, in the near infrared, you get very quickly saturated in a way in terms of flux for very close inner radius because the rest of the disk doesn't really emit. Then when you look at near-infrared, so 10 microns now, you get further out because the temperatures that trace mid-infrared emission can go further out, but you're still missing a ton of the disk, which is what sits in the outermost regions. And the outermost regions can be well described, can be well traced, by the long wavelength emission, because there we see the entire bulk of the disk. And so you can see it here that when we look at the cumulative flux at long wavelengths, it looks much closer to the cumulative mass of the disk. And so we can better probe what is the mass distribution in this object. And another way to look at is we can have exactly the same young star. So here's the spectral energy distribution of the star, and here's the excess of emission from the disk. And I only change the disk mass by 1 order of magnitude. So a disk mass that is 0.1 solar masses or 0.01 solar masses or much, much smaller. And what you see is that although in short wavelengths we have no clue and they all look the same in terms of spectral energy distribution, at long wavelengths they completely separate. And we can tell that the most massive disk here in blue will have much more emission, an order of magnitude higher than the less massive disk that is 1 order of magnitude below in terms of mass, and then 1 order of magnitude again in terms of mass, and then in terms of flux. And this is because we can write that the observed emission at long wavelengths really directly relates to the total disk mass. Okay? So, as I said before, we can probe different regions of the disk looking at different wavelengths, and we can get critical constraints on the structure and the distribution of the material as well. So far we've looked at this in a more idealized, smooth form. But if we were to probe with mid-infrared emission, we will probe a bit deeper, but still closer to the central object. If we look in the near-infrared, we will see emission here in yellow from the inner part, but also all the way to the outermost regions of the disk. And what happens is because the star is directly illuminating that atmosphere of the disk. And that direct illumination means we see the emission right away. And when we look then at millimeter centimeter wavelengths, we can really get down to what we call the midplane of the disk. So this, the place where we think planet formation really takes place, because this is the most dense and most cold regions in the disk. And remember, you need things to be cold if you want them to coalesce. And I wanted to point out here what the instruments do. And so here is, as a function of distance on a logarithmic scale, with ALMA, you can certainly probe, depending on the wavelength that you look at, from 3 millimeters to a fraction of a millimeter, you can probe down to very close in to a star. So you could really see the structure at 1 AU resolution, which is amazing. With an instrument like VLTI and Matisse, you could get down to also those regions, but this requires interferometry techniques, okay? And then with the future extreme telescopes that will be put forward in different places around the world, and this is just one of them, the ELT, you really also can probe down and match, in terms of angular resolution, what we see already with ALMA, okay? And then I wanted to point out that the corona from the star also emits in X-rays, and so we can see the variability and the flares that these young stars have if we look at them in X-rays. And in optical and UV forbidden lines, we could also see the process of accretion, the material flowing from the disk onto the star, which is also highly variable. But the bulk of this talk will be dealing with these observations of the actual disk. And one more set of observations that one can have that can be looked at in the radio or also in optical forbidden lines is the fact that the photons from the star will disperse the disk from its atmosphere. And so we see this wind, that we call disk wind, and we can trace it also with some long wavelength observations and with optical observations. But the lesson here is that when we go at millimeter and centimeter wavelengths, we can trace the bulk of the mass. Because it's optically thin, we can see down to the place where planets form, the midplane. And current facilities like ALMA and the very large array that I will discuss in a second will cover from very close to a central star, 1 AU, all the way to the outermost region. And yesterday I showed this that we can trace the gas component in molecular lines and the dust component in thermal dust emission. But something really cool about long wavelengths as well, you see why I love them, is that we don't care about contrast. Because remember, the stellar SCD was really down low at the very long wavelengths, where the excess of emission was from the disk. Because the central star has barely any emission at millimeter wavelengths compared to the huge emission that you see from the disk. While if we look at a disk at 3.8 microns, there is still quite a bit of radiation from the protostar. So we have to use this technique when we occult the star. That creates a mess in the, you have to know very well your PSF to be able to trust what you see. And so you don't know really if you're probing the outer disk region or some PSF issues in this type of observation. And so here you can see is exactly the same disk, the famous HL tau. And if I told you which one do you want to use to understand the distribution of solids in the disk, I hope you agree with me that you would like to go to long wavelengths, because contrast is not a problem. The star is invisible. And ALMA and the VLA have been really transformational to the field and have shown us that these disks are full of structure and are full of features that theory sometimes had predicted and other times had not predicted. And that for some of them, we can nicely explain with the presence of planets. But that will be tomorrow's talk, okay? So we will move on to these first steps of planet formation. So we want to make a planet, and our initial material is sub-micron size dust from the interstellar medium. And we want to grow it 14 orders of magnitude to make a planet, okay? 14 orders of magnitude. So a lot has to happen. And we have some parts of the picture worked out, but others are still a work in progress. When you are in the small sizes, particles stick to each other due to van der Waals forces, electrostatic forces. And you can see some simulations, numerical simulations of the process here, where you can see how growth of two different aggregates starts to get larger and larger as time goes by without much trouble, as long as these collisions are very gentle. Generally, these very small aggregates, you know, the sub-micron sizes, are moving in Brownian motion embedded in this gaseous disk. And so they find each other and they collide quite gently. And this growth can proceed if this one collides with a bigger one, it will proceed again and maybe some compactification will occur, because maybe now the velocities are larger between them, and so this will get a bit more compact, and the collision will still permit this grain to grow to larger sizes. And this, you can imagine, can happen for different grain sizes, and people have tested this in the lab, and it really happens, but up to, you know, a millimeter and maybe even a centimeter, but really millimeter. And it's because, you can imagine, try to make two pebbles, try to collide with each other and grow to something larger, it's hard. It's not easy. Maybe if you coat them with a little ice, which happens in different places of the protoplanetary nebula, then maybe you could get them to collide and stick and grow to larger sizes. But in general, given the velocities that these particles will have, the differential velocities, this collision will start becoming destructive once you have reached a macroscopic size. So you cannot get this growth to proceed further through this gentle particle-particle stick, okay? In between then, there is a big question. How do we go then from these macroscopic particles to something like a planetesimal? And there are some ideas of how this growth can proceed. And one of them is that we have instabilities in the disk that we can generate that will create pockets, regions in the disk, that will have much higher density than the rest of the disk. And these regions of high density, you could really create very large aggregates and grow to planetesimals very quickly. But there are other ideas as well, and this is something that we are in the process of trying to understand. What of these ideas, what are the observational predictions, and do they match what we see or not? And then on the other side, once you become so large that you can enhance your cross-section, which should just be your area, right, your cross-section, thanks to gravity, because you're large enough that you can attract material from further out, like in this diagram here, where your cross-section is enlarged, then you can just really grow very quickly and attract a lot of material. And this happens in a sort of runaway growth. And this is just an animation, it's not a simulation, where you will see that then this massive object will clear out a path and will start attracting a lot of material around. But again, this is an animation, not a real simulation. And so, as I said, what happened in between is not well understood. But I have one piece of good news, and it's that these pebbles can be detected at these long wave observations. And this is because a pebble, you can imagine it like a little antenna, okay? An antenna that has this size will be very efficient at emitting signals that are about the size of the wavelength and at receiving signals that are about the size of the antenna, I'm sorry. If you have a signal that is a wavelength much larger, this little antenna will not be able to focus it. If you have a signal that is smaller, you will be much better able to focus the signal up to the size of this little antenna. And in the opposite way, you have this little antenna and you want to emit radiation. You will be able to emit radiation with this antenna that is a wavelength close to the size of the antenna or shorter. And so these pebbles that are about a centimeter in size emit the bulk of its radiation at centimeter wavelengths. If you have a millimeter pebble, then you will emit the bulk of the radiation at millimeter wavelengths. If you have much smaller particles, you will emit radiation at smaller wavelengths. And so you can really probe, and we will see some of these in a future slide, you can really probe the presence of millimeter and centimeter particles if you look at millimeter and centimeter wavelengths. And these pebbles is the last direct detection of solids before we detect an exoplanet, right? This is your last shot. You get to detect them at the millimeter and centimeter size range, but we don't have the sensitivity to detect the emission from kilometer-sized bodies. And so this is it. We can detect their influence in the disk, but we cannot do a direct detection. And so observations at millimeter and centimeter wavelengths really let you probe the distribution of solids at the moment of planet formation. And so this certainly will inform our knowledge of this process. So how is these solids evolve in the disk? In the very early stages, which is what we're discussing today. Well, the evolution of solids is really modulated by the gas. And the way the dust is transported in the disk will impact the way it grows. So at the beginning, when you have small particles, you can grow through turbulent mixing. And when I talk about small, I'm talking about much smaller than a millimeter, okay? So micron sizes, things like that. Those particles fill the gas and move with the gas, and the gas has some turbulence. And so these particles gently find each other and grow to a larger size, as I shown in that numerical simulation. And so with this turbulent mixing, you start growing and growing and growing, and you can quite quickly become something large, like a millimeter or so. The problem is, once you become that large, in the outermost regions of the disk, you start feel that you are heavy. The gas cannot provide pressure support. You're heavy, and you start running towards the midplane, the place where most of the mass is sitting, the mass in gas. And so you feel the gravitational pull, and the gas pressure cannot give you support, and so you start moving towards this midplane. As you move, you start accreting more and more particles, and you can really grow very efficiently to something like a planetesimal within this framework where we've only considered these two ways of growing: turbulent mixing and vertical settling. And when you look at what's the solution from just considering these two ways of growing, you can really get the building blocks of planets. A midplane full of planetesimals, rocks, pebbles, that then you can use to form the rocky cores of planets. So the problem is solved, so why are we here? Because we forgot to consider the modulation by the gas. The fact that the gas has some influence in this process of growth. And to discuss this, let's imagine here is a protostar, here's the protoplanetary disk. I'm just showing 1/4. Here's one orbit in the disk, and here's your solid particle. Well, the solid particle is clearly dominated by the Keplerian orbit around the star. And so it orbits at Keplerian speeds because it only feels the force of gravity and the centrifugal force, and orbits in a Keplerian orbit. But if you have a parcel of gas, this parcel of gas feels the gravity, feels the centrifugal force, but also has some pressure support because gas has pressure. And that means that instead of having a Keplerian speed for the orbit where this parcel of gas is, it has a slightly sub-Keplerian speed because there is this extra force that you have to take into account for this parcel of gas. That means that the gas is moving at a different velocity than the solids. And what happens with that? It's like traffic jam, right? And this problem, it's a well-known problem in planet formation, and it's called the radial drift of solids. And it was really postulated before we knew about exoplanets, before we knew about protoplanetary disks, before we knew a lot about young stars. And it was just the scientists thinking about how do we make the solar system ourselves from this protosolar nebula if we have to consider the fact that the solids and the gas will move at a different speed. And the equations that describe this are somewhat simple, and they just show that when you are a small particle, you just move with the gas. The gas moves one way, and you move like a leaf on top of a river, you know? But if you're a big particle, you want to move Keplerian speed, and the gas is moving sub-Keplerian. So it means you keep running into the gas because you want to move faster, and the gas produces a drag in this particle. When you feel a drag, you lose energy, and that means you lose angular momentum, and you move to a smaller orbit. In that smaller orbit, you're closer to the star, so there's more density there, so there's even more gas to feel more drag, so you lose more energy and more angular momentum, and you move to a smaller orbit. And then you keep doing this over and over and over until you end up where? Here. So although we grew a large particle, or maybe a small particle, a centimeter size, these particles will feel this aerodynamic drag from the disk and will just radially drift, that's where the name comes from, eventually, I mean, it will be a spiral, but overall will be a radial drift towards the protostar. And so you grew your grain, and then you lost it. And maybe it won't be such a big deal, but turns out the time scale for this process, given the huge, it was 100 times the mass in gas versus the mass in solids, that this time scale happens very quickly. It can happen in 1,000 years, which is much, much less than the million years that these protoplanetary disks are living there. So that means there's this big problem to grow larger particles, because if we grow them, they will feel this aerodynamic drag and leave the disk. They will just go to the protostar. And this drift velocity, if you calculate it, and there are some beautiful papers about this, and I recommend the ones by Till Bernstiel because it has all the equations laid out. And there's also a nice review. Sorry, I didn't put a slide about this. From Phil Armitage. Phil Armitage wrote a book about planet formation. And you can buy the book, don't buy the book. Get the archive version online, because Phil keeps updating it with every new thing and every new result, and so it's wonderful. So I promise I will make a slide for the next class with the advertisement for that. And so when you look at these equations, which are in these reviews, for example, what you realize is that this radial drift velocity, so the velocity that the solid will end up going radially, depends on the pressure gradient. So the drift always occurs towards the place where the pressure is maximum. And in this disk, remember, there's a density gradient. The pressure will be maximum closer to the star, and so the drift will go in that direction. So, okay, so if we consider this radial drift of solids, we also realize that it's not equal to every particle. Depending on where you are in the disk, you will feel a different aerodynamic drag, because there's a density gradient in different regions of the disk. So further out, you will be less dense, but then you will mostly affect the centimeter and millimeter sized particles. You see, this is the drift arrow here. And so once you become large enough, you completely decouple from this issue. You're large enough that you don't care what the gas is doing. You do what you want. You're a planetesimal. You don't care. You continue in your orbit. But this radial drift create these barriers, which are the barriers that were put forward in these very early papers. And really, back in the day of Whipple, it was called the meter-size barrier. So you have a meter size, a boulder that should help you get to a rocky planet, will not be able to survive for 1,000 years at the location of Earth at 1 AU. And so people say, well, maybe this is not a problem, because we still have all the small rocks and pebbles further out. But if you do the calculations, the centimeter-sized particles will not be able to survive, within 50 to 100 AU either. So this affects different particle sizes at different locations in the disk. And in the overall result is that we lose the solids. And we need the solids if we want to make rocky cores of giant planets or planets like the Earth. Finally, there is one more issue, that the evolution of the solids in disk depend on the properties of the solids itself. And the outcomes of the collisions within the disk will depend on the structure and the composition of the grains. If you have these very fluffy grains that collide with each other, well, they will just compactify, but you can imagine them continue growing. If the grains are really completely solid, you can imagine that even gentle collisions might result in bouncing, so they just bounce off each other like balls, or fragmentation. There are other ways you could do a little bit of mass transfer. So even though you didn't grow to a full solid, like in option A, and you didn't bounce, so bouncing is good because you didn't lose the large grains to begin with, maybe you can transfer some mass, and the last option is just completely fragment. And so you have to consider all of these to be able to understand how do you grow these particles in the future. And there are people doing these experiments in the lab where they simulate the protoplanetary disk conditions and bounce rocks off each other, which is really cool. And I'm always jealous of the people that get to do this. So here's an example where these two particles actually stack to each other. given the conditions, as I said, like a protoplanetary disk in terms of vacuum and velocities of these particles. You could also have some mass transfer. So here you didn't really see it, but there are these two particles, and although they fragment, some mass is transferred from one to the other. Then you can see here how, although it's a gentle collision, you will see it in a minute, they bounce, so they don't really stick to each other. So that didn't help us grow to larger sizes. And then finally, you can completely fragment, and you can test the material strength by trying to fragment different things and say you have to be this strong for this velocity to allow for further growth. And so these, I recommend there are several papers by this group, Jürgen Blum. This is one annual review, but there's a more recent one that really shows some of these beautiful laboratory results. But you don't only have to go to a lab, you can model all of these because these all follow some equations that you can solve for the hydrodynamics of this process. And this is really an active area of research, and it's been providing predictions for these particle size distributions versus radius for different conditions. And so I'm going to just show you a few simulations. And so this is just one snapshot for a disk that is quite massive with some turbulence and a fragmentation velocity of 3 meters per second. So anything that goes, any two particles that collide at velocities larger than 3 meters per second should result in a fragmentation rather than growth. Okay? And what I will be showing in these plots is really grain size here in this axis. So we start with something that is like the ISM, micron size. Then we grow to something like a pebble, and maybe eventually we get to planetesimals. And in the x-axis, what we're showing is distance from the star. So this will be 1 AU, 10 AU, and 100 AU. And these colors represent density of solid particles. So, you know, these white colors will be very dense, these light colors will be less dense, and then the blue will be much less dense, and then black means nothing. There's no solids there. And these are some simulations based on these nice papers that I was telling you about from Till Bernstiel. And as I said at the beginning, if we don't turn on this radial drift problem, we don't consider this barrier, and we don't consider fragmentation, meaning any two particles that touch each other will grow. Not considering this, well, you get growth from interstellar medium light grains all the way to planetesimals at every location in a disk. So why is there a problem if you only consider these two things? Because you can have then these planetesimals to form this rocky core. And the issue is that if you turn on the radial drift, you will see that it will not saturate forming planetesimals, but it will form much, much smaller particles. Because although you grow them, you see that they start leaving the population over and over and over, over and over and over. Until at the end of the day, maybe within 1 AU, you have some pebbles, but between 1 and 10 AU, you really have much less dust than what you should have to begin with, and there's really no option to form large bodies out there, okay? And if you turn both things on, so this fragmentation, the fact that, because here we still say every two particles that touch will form something, here we turn the fragmentation barrier on, you see that it becomes really strong. And this fragmentation barrier you will see drawn here really does not allow anything to go beyond these sizes, and then radial drift will take over eventually. So here is the fragmentation barrier, and then the radial drift removing the particles. And so at the end of the day, you miss the large bodies that will eventually make the rocky planets. So this is bad news. So not only we don't know how growth proceeds from, you know, macroscopic particles to planetesimals, but we are also faced with these two barriers of growth. And this is something that I have been interested in since my PhD, and one way to explore this is through radio observations, and we have this collaboration that has put forward many different results related to this, called the DISCARI VLA, to study this issue of grain growth. And so the PI is Claire Chandler, which is at NRAO, and with her, we managed to obtain this large, beautiful data set of DISC, and we published a whole bunch of papers. And I'm trying to get some new results with a undergraduate student, on this topic. And really, this was only possible because the VLA did an upgrade to upgrade its sensitivity. So why did, the VLA is an old telescope in a way, meaning there were movies about it. Have you seen Contact? You should watch it. It's a great movie. And so it's an old telescope. Why people didn't do this before? And it's really because it will take months on the telescope, just on one target, to look at this. And when we did this survey after the sensitivity upgrade, which means they changed all the internal electronics, but the metal in the ground, the antennas stayed the same, we were able to get this large number of targets in a much shorter, much less than a month time scale per target. And why do we want to go to centimeter wavelengths? Because these long wavelengths can help us constrain the dust property. So here I'm showing the opacity for a single dust grain that has a different size. You know, if you're less than a few microns, you start having all these weird resonances and special things, and then you drop in terms of emissivity, okay, as a function of wavelength. So you see here, this is frequency because we like frequency, but wavelength is up here. So 1 micron, 10 microns, 0.1 millimeter, 1 millimeter, 1 centimeter. But as you become macroscopic, something that you can look with your eyes, you're really equally bad, I guess, to emit at all wavelengths, except when you get about the wavelength of your size, and then you become really bad. It drops, your emissivity drops. Then when you go to 1 millimeter, it's the same, 1 centimeter is the same. What I'm trying to say here is, if you look at 1 centimeter, the emissivity will be poor, and then it will drop even further. But when you look at 1 centimeter wavelengths, the biggest emitter are the 1 centimeter particles. If you look at 1 millimeter, well, the 1 millimeter particles are quite bad, and then they become even worse as a function of wavelength, but they are the biggest emitters at 1 millimeter. If you look at the 0.1 millimeter, it's the same. 0.1 millimeter is sitting here, and it will be better at emission than the other particles. And so every particle, in a way, provides the most emission at the wavelength that is comparable to its size. So the first lesson is, if you look at observations that are of a wavelength A, then they will probe grains of size roughly A. There's a factor of 2 pi here, but we're astronomers, we don't care about 2 pi. And then the opacity for a grain size distribution, because of course there is not a single grain size in a disk. There is a grain size distribution from submicron all the way to centimeter sizes. For a grain size distribution, then you start having these curves here, which are the standard opacity curves that you know of. When you stop, like in the ISM, in 1 micron, the largest particles you may expect, you have these red curves that sharply drop at long wavelengths. But as you increase the maximum grain size that you allow in your population of grains all the way to 1 meter, what you see is that from steep, it starts becoming flatter and flatter at long wavelengths. So at long wavelengths, you can probe, the emissivity probes the maximum grain size with this parameter beta, going from quite steep, so it will be a beta of 2, to much, much flatter values of this parameter. And why do we care? Well, because the observed emission just goes as a modified black body, modified by what? By the emissivity or by the opacity. And the black body at long wavelengths just goes as this Rayleigh Jean approximation, so nu squared. So there's your nu squared. And your opacity at long wavelengths goes as nu to the beta. So really, you just have to take a lot of observations on multiple wavelengths, measure the spectral index, so measure the spectral energy distribution, and you could try to figure out what's the maximum grain size. So from long wavelength observations, you could measure a grain size. So the second lesson is, when you measure the spectral index, you're probing the maximum grain size, and you're measuring the spectral index by measuring observations at multiple wavelengths and fitting for this globe. It's a bit more complicated than that, but in this picture, this is good enough. And before I got into this field, we knew this already. When we looked at many, many studies with many, many different telescopes, when we measure the integrated spectral index on disks, is smaller than the integrated spectral index in the ISM, meaning the ISM will be this really steep spectral index, about 2, and the spectral index of the disk was much shallower. And that change only takes place when you increase the particle size, as you go to larger and larger bodies. So these studies told us, well, in disks, you don't have your ISM solids. They have grown to at least millimeter and centimeter size. Okay? So these unresolved observations imply at least 4 orders of magnitude in global growth. Global because they are unresolved. We don't get to see, as a function of radius, what the disk is doing. We just see one data point for the flux at that wavelength. And these 4 orders of magnitude imply that, at least from the interstellar medium micron sizes, we've grown to pebbles, centimeter size. So that's great, but from the simulations that I show you, the simulations here, we will expect that the grain size, remember this was grain size, change as a function of radius. The maximum allowed grain size will be, centimeter close to the inner star, and maybe micron size further out, depending on how strong is radial drift or how strong was the fragmentation, etc. So there will be a max as a function of radius that will be allowed by these processes of radial drift. And this maximum grain size, I told you, relates directly with this value of beta that becomes interstellar medium-like, so 2, when you have small grains, and becomes very flat when you have large grains. And so this means that this process of radial drift should leave an imprint in this measurement of beta. And people try to do this. People try to do this many, many times. There are a few authors here mentioned. This is just a plot of many different disks. But what you see is that even within 1 sigma, you are consistent with a constant value of beta throughout the disk. So something that will be flat, like this. Not this radially varying beta that we expect from these numerical simulations of the process of drift and fragmentation. And the problems here were they didn't go to centimeter wavelengths really, they didn't have the right sensitivity, and they didn't have the spatial resolution. It was really 1 point in the inner disk and 1 point in the outer disk. And the solution was what we found with the discrete VLA. We have wavelength coverage from the submillimeter to centimeter, and that allows you to measure better the spectral index. We have high sensitivity, and we can get down to tenths of astronomical unit resolution. And so here are some of the disk VLA papers and the gradients that we see. Every disk has a slightly different gradient. You see here the gradient of beta for this simulation, and here the gradient of beta actually measured in the disks. So there is a change from these ISM-like values of about 2 in the outer disk all the way to something related to large particles, a much less steep value in the inner disk. And so we can do sorry, I'm going to skip this 1 sec. So we can do this and back out then what will be the maximum grain size that is allowed in the disk as a function of radius from the observations. So this is an observational constraint. And the observations tell us you cannot have, centimeter grain sizes between 1 and 10 centimeters, except for within, 20 AU. So you cannot have large particles, and you can have about half a millimeter or less in the outer disk. But this is from observations. And what was new here is that we decided to then combine it with this theoretical prediction. So what does theory tell us? And when you look at the radial drift barrier, you see that it really matches very nicely the constraint from observations. So large grains are allowed in this disk closer in, and they are not allowed, you see this is empty, in the outermost regions, because if they grew, they radially drifted. They left the population. And we draw here the fragmentation barrier with standard assumptions. And the standard assumptions mean that there should be no grains here, because the barrier sits down here. You could change this standard assumption having a disk with very low turbulence so that the collisions are really, really gentle instead of very high turbulence where the collisions will be. And our standard picture is that there is high turbulence in disks, and collisions should occur very energetically, and then the fragmentation barrier should be down here. You shouldn't really have very large grains. But at least from our measurements, we think, no, the turbulence should be very gentle because it should be very slow and the collisions should be very gentle. Or on the other fact, your grains are made out of iron or something, and that way they survive strong collisions. In order to match this observational constraint that we made here. And what is interesting, though, is that these are something that I work on when I was a postdoc, but now current measurements of turbulence in disks keep showing that turbulence is actually low. We cannot get to it's so low that we cannot get to measure the amount of turbulence there is. So our previous mindset of high turbulence in disk might not be correct and matches the prediction from this type of observation. So what I wanted to end up pointing out is these barriers of growth cannot be ignored. You cannot ignore the fact that radial drift and fragmentation take place in a disk. So what have we learned in this part? Well, the building blocks of planetesimals are present because we see centimeter emission, so we know there are centimeter-sized particles in these regions. There is a radial segregation by particle size. The largest particles are found closer in, and the smaller particles are found further out. And these observations appear to be consistent with these theoretical predictions of barriers of growth. So these are the three things that we know now. And this sounds bad, because these barriers of growth do not let us go from millimeter to planetesimals. But nature somehow has to overcome all these barriers because we live on a planet. So at least we know planet formation took place here. And we know of a ton of exoplanet detection. So this process has to be overcome somehow. And so I wanted to point out that, and we will talk about this tomorrow, but I will give you the answer today, that as we saw, the evolution of solids is modulated by the gas. And if you have a disk that doesn't have any substructure, so it's a smooth surface density with a pressure gradient that just points towards the center, and remember the drift velocity took the direction of the pressure gradient, so it was pointing towards the center, these solids will just get lost as before. So they will grow. This is a different setup, so they don't even make it to pebbles, and then they get lost, okay? But if somehow there is some substructure in the gaseous component in the disk, so why does it have to be smooth? I guess because we didn't look at ALMA images before knowing what they were, that they were not smooth. But if you have some substructure, you could trap at the locations of pressure maxima your solids. And so some of them drift, but some of them remain trapped at the location of pressure maxima. So pressure maxima can become like a safe haven for these particles to grow further and form even larger bodies. And so we now think that there might be some connection and some maybe 2-generation planet formation. You may have planets forming here already by some other process, that then creates substructure, and this substructure protects the rest of the solids from leaving the population. And how is substructure created? Theoreticians are incredibly creative, and they give us plenty of possibilities, plenty of ways like I'm showing here, but we're not going to talk about this at all. Tomorrow we will talk about what theoreticians say. Oops, what happened? Microsoft has encountered a problem. Okay, try again. We're just going to talk about the very last part, which was what do we know, not from looking at substructure, but from looking at surveys. So what do the surveys from ALMA tell us? So there is beauty on this that you cannot imagine. When I was a grad student, we could do a handful of these objects, and it will take forever. Sorry. And now you point ALMA for 10 seconds per young star, and you get these hundreds postage stamps observations of all these disks. Really beautiful. And here I'm just showing two recent disk surveys in Ophiuchus and Lupus from Lucas Ciesa in Chile. But there are several other surveys completed in this famous star-forming region. And so we look at a few hundreds of disks in regions that are, a few million years old. Okay. And we know from infrared excess, so this is known from a really long time, that there is a decay in the disk frequency. So disks are not found so commonly as the age of the cluster becomes older. So older clusters shouldn't have disk, planet formation took place, blah, blah, blah. But in young clusters, you will have 80% of the stars with disk. And we can look at this in a different way, because this, remember, infrared was optically thick, only the inner regions. So this was only telling us a very small part of the picture, while the radio gives us the more complete picture of the entire amount of solids. And what we see here, so these are just the cumulative distributions of different star-forming regions that get older and older from red to green as a function of the mass available in solids. And what you see is this evolution. The younger regions have much more mass available than the older regions. So there is some evolution of the solids. Maybe the solids are going into larger solids that then we cannot probe with centimeter and millimeter emission. Other basic properties that we've seen is even precursors to ALMA, we saw this correlation of the disk mass scaling with stellar mass for the low mass stars. So, the brown dwarfs will have a smaller disk, the normal T-Tauri stars will have normal disk, and then the really weirdos will have a larger disk. When we look at Taurus, for example, we see that the median disk mass is about 0.03% of the stellar mass. So it's quite small disk mass. And we still see this correlation. But in older regions, the correlation appears to get lost. So this is upper scope, which is maybe 10 million years old, and the correlation is gone. When we look at now ALMA surveys of this, the correlation gets tighter and tighter. So there is something going on. The disk stellar mass, the disk mass and the stellar mass is correlated, because remember, they form from this process of star formation. So there has to be some relationship between the two. And another maybe obvious but interesting to check thing is that the emission at millimeter wavelengths scales with the area of the disk. This gives us a sense that, okay, we are optically or close to optically thin, because we are measuring, if you have more emitting area, you will have more luminosity. And so there is this nice relation. Finally, here the fraction of sources as a function of age. So when you go to the early age, remember that I had this diagram with the protostars, with the outflows and stuff, and then it was evolving out to a protoplanetary disk, and then, well, this is just that, but with classes. We like classes. As a function of age, you see that the bulk of the material gets lost too. But it's only been shown in one star-forming region, but there's a large sample, so maybe it's true. Is there enough mass to form our solar system? Well, before ALMA, we looked at some disks with interferometers. It really took a really long time, and it was not an easy feat, and here's one of those papers. And you can see that these guys appear to have, I mean, there is a huge uncertainty in what the minimum mass solar nebula is. But these are the most massive disks, because that's the ones that we're going to look at with the bad interferometer, with the precursors. So maybe there is enough mass, but are we looking at the tip of the iceberg? And when we actually look at older clusters and when we look at the entire population, we really see that the vast majority of disks are below the minimum mass solar nebula. And another way to look at this, I really like this review and this paper, is we can ask the question of, is there enough mass to form the known exoplanet population? So we will count the disk mass in solids and compare it to the known exoplanet population and the minimum mass on our nebula. So here is the class 1 disk, so the young disks, and here are the protoplanetary disks in black. And the solids in planets and in debris disk appear to be, in, at least for more than half of the population, be more massive than the mass in solids in disks. What the hell? So the egg is larger than the chicken. That cannot be. But maybe in these disks already, planet formation took place. And the solids are just hiding in planets, and we're looking at the wrong population. So this is why I was telling you at the beginning, we shouldn't talk about protoplanetary disks, but rather planet-forming disks, because the planets are there already. So this is a hint of this, but certainly the field has not agreed to any of this yet. And here is the minimum mass solar nebula with a range, and you see that it's really the tail of the population that can be like the minimum mass solar nebula, so only a few percentage. The impact of the environment, I'll just say briefly, yes, being close to a big, massive star really hinders your possibility of having a large disk mass. So this is the distance to Theta 1 Orion, a massive star, and being close to it really kills your protoplanetary disk. What about binaries? And because there were some questions about binaries yesterday, when we look at the distribution of single stars, well, the distribution of single stars here in blue looks very similar to the distribution of the white binaries, binaries that are so far apart, you know, thousands of AU, that they're like two different stars separated, but having an orbital motion. So it's like they don't perturb each other, they don't do anything. But when we look at the close-in binaries here, so as you get your two stars closer and closer, the distribution here is really different. So being in a binary may hinder your planet formation potential. Except, of course, these weirdos here. These weirdos here have so much mass, but they sometimes are in really tight configurations, and we don't understand those. For binaries, we also see this scaling with mass, and because of time, I think I will skip this, but there are very interesting issues with binaries that you can read in this paper. So what are the open issues here? Well, what we will discuss tomorrow, what do resolved observations tell us? So these are simulations, these are not real data. I will show you a lot of real data tomorrow. Do the substructures correlate somehow with stellar properties? So here are some, you know, from A to M stars, A, G, K, M, and we skip some Fs here. But, you know, do the substructures that we see correlate somehow with stellar properties? Because that can tell us about the exoplanetary system that will form, maybe correlate with the properties of the host stars, right? It's an open question in the field of exoplanets as well. What about astrochemistry? I will show something in 1 second. We didn't talk at all about this, but somehow the precursors to life have also to be found in these protoplanetary disks, okay? And the question that I pose at the end, are we looking in the right place? Maybe it's not the really evolved protoplanetary disk. Their planet formation already took place. Maybe we have to look to the younger class 1 sources, and this is an open problem right now. And the one slide I'm going to talk about in the future, and with this I finish, is tracing the chemistry during plant formation, which has big, important implications in life. And there is this Alma large program, Chemistry of Plant Formation, for which Professora Viviana Guzman at Universidad Católica, so she and I are very good collaborators, and I'm part of this collaboration as well. She's leading from Chile, and they will be looking at these 5 protoplanetary disks that have very interesting substructures, and they will be looking at the chemistry of it. With ALMA, molecular line emission, to understand things related to the distribution of organics, really important for life, or the location of the snow lines and things related to grain growth, etc. There's also a lot of kinematic studies you can do. And she's always looking for students, postdocs. If you want to work on astrochemistry, even if you have worked on something different before, contact Viviana. She's great. So this is my last advertisement slide, and I will stop. Thank you.
Thanks, Laura. Questions?
So, thanks for the lecture. And so, what's the temperature and pressure? I don't know if you know, and the simulations in protoplanetary disks before the collisions and after the collisions, something changed?
So first, related to the temperature, as I said at the beginning of the talk, we're talking about the temperature. What defines the disk in a way is the location at which the dust sublimates. So really has to be 1,000 Kelvin or much more, 1,500, so 1,500. So that will be the innermost regions of the disk. We're talking about those temperatures. And then in the outermost regions that are not directly illuminated by the star, we will be talking about, you know, cosmic ionization heating, for example, and we'll be talking about, you know, several Kelvin, okay? So very, very cold. So the chemistry, for example, it's very well influenced by that, and this becomes a big problem. And the second question was about collisions, about the fragmentation in the models?
Yes.
So the fragmentation can actually be treated analytically. So really is you set a velocity at which if 2 particles collide, this collision results in a fragment, not a growth. And which you have measured in the laboratory from these experiments, and of course depends on you know, if your grains are very porous, they probably will fragment at much lower impact velocities if they're very, you know, completely solid grains, if they're coated with ice or not, etc. So it all depends on the different conditions, but on the properties of these grains. But one way to just forget about these properties is just set this fragmentation velocity, because the fragmentation velocity will be driven by the properties of the grain, but we can probe different fragmentation velocities and try to understand what matches the observations or not. So in a way, it's a proxy. So that's how it's treated.
Okay, thanks.
Thank you for the lecture. How do these models take into account the formation of systems with satellites, or how does the prior presence of systems with satellites affect the formation of new objects in the disk?
So you're talking about during the formation process, if you have a satellite. So we haven't really talked about now building big things. We talked the early stages today, and hopefully tomorrow we will talk more about building big things. But this is a great question, because in some of our theory, we show that you would expect around any of these big massive objects that are forming there, something like a Jupiter, for example, to a circumplanetary disk to form as well. And this circumplanetary disk, which will feed from the circumstellar disk will fit material onto the planet, this circumplanetary disk should be able to form satellites as well. And this process of radial drift should be even more enhanced, given the high densities that we have there of gas. And what people have thought is you will actually have a hard time detecting circumplanetary disks at long wavelengths because you probably lost the pebbles much more quickly. But we just had a paper we submitted. Maybe I shouldn't, people are recording this, so I don't know, but where we think we see this, where we see the evidence of a circumplanetary disk in solids. There is some evidence of circumplanetary disk in gas. So yeah, so this is really the edge of the current status of the field.
Thank you.
Hi. My question is, the spectral type can be important in the ground of the pebbles or the grain?
So you mean for the process of radial drift?
Yes.
So certainly in terms of the disk mass. So you saw how the stellar mass and the disk mass correlate. So more massive stars, or Herbig AB stars, for example, will have more massive disk than brown dwarfs, M-type stars. And so the mass of the disk will correlate with the spectral type in a way. And then the mass, not only the mass, but the size of the disk too. So you will have smaller disks around smaller, M-type stars compared to the Herbig AB stars. And this all creates correlations with the process of grain growth and radial drift that are different from what you might expect. Turns out in brown dwarfs, the process of radial drift might go even quicker for the pebble-sized particles. But we know of planets in brown dwarfs, so something has to be stopping that for the brown dwarfs. And in the Herbig AB stars, we see a ton of substructures. Those are the most beautiful substructures in disks we see around those stars. And these substructures is the way to stop this drift. So maybe this is a very common process that can be stopped easier on the high mass stars. But this is all me speculating because we don't have large enough samples to know this. And so I put this as one of the questions for the future, that we need to know how this correlates with spectral types, for example.
Hello, thanks for the lecture. I have a question about the grain size and collisions. You said 2 grains of pebble from the same sizes usually collide destructively. But it's possible to a pebble to accrete or other smaller or dust
Certainly.
and grow this way.
Certainly. So these are different pathways to grow as well. And the simulations generally take into account these pathways of growth. But I was talking about the largest barrier is the collision between similar size aggregates because they will be big and may collide and fragment. So the growth certainly can go in the way of mass transfer, so from one large one, a smaller one. But when they're equal size is how you lose the particles. And we are worried about losing the particles a lot because this is how these particles that get lost are the ones that you need to make the planet. So this is why we consider this in particular.
Okay, we have time for more questions. Questions, comments?
People are ready for lunch.
Everyone ready for lunch? That's it? Okay. So let's thank Laura again. Marco just has an announcement relative to the program.
Yeah, if you can find on the notebook the program and the program notebook and the website tomorrow is a bit different, but that's because there was our mistakes. So tomorrow the first lecture will be Vivian Miranda, cosmology. The second lecture will be the same. I think it's Laura, and the third one will be supermassive black hole lectures with Franz Bauer. So the version on the website is the correct one. So you can check the program on the website if you have doubts.